All right, everybody. And you can just. We'll see.
Didn't even work that much time.
All right, everybody. It is class time now, everybody. So today, first announcement, the one that's on the board. Guess what?
That's on Wednesday.
Test is now on Wednesday.
Yes.
It's easier that way. Okay? Since everyone's going to be gone. All right. Canvas has been updated accordingly. So now if you go on Canvas, it says the test is on Wednesday. Assignments have been shuffled around so it all makes sense. Everything like that. Okay? All right. Thing we're going to start off with is any questions anybody has about the homework from last night. Okay, yes, Teddy.
57.
57. Okay. Hold on a second. You all right? Okay. 57. This is the one that looks like. Hang on. Is this? Yes. 57, and actually get it up to class. Okay. Is this 57 1.2?
What?
Which 57?
1.2, yes.
1.2. Okay. All right. Your homework for tonight will have the same numbers, but will be 1.3, and I'm just making sure I got the right class. Okay. So 57. Okay. What we've got here is we need to figure out. Basically, we want the limit as x goes to, what is it? 4 of the square root of x plus 5 minus 3 over x minus 4. Okay? Now, the thing is, if we stuck 4 into this right now, what do we get?
0. Doesn't work. Right?
0 over 0, right? And what does that mean, remember?
That's an indeterminate.
Indeterminate. Something else is going on here. Okay? Now, as it currently stands, we could try to do this one by hand. It would not be pretty. Okay? This is not something easily done by sticking 4 in and getting an answer out. Okay? It's ugly. The directions, though, tell you how to do it. They say, use the graphing calculator. So what are we going to do? Use the graphing calculator. Okay? So we'll bring up the graphing calculator.
Yes.
Come on. Yes. Up. Way up. There we go. Okay? And we'll go ahead and we'll graph this function. Okay? So, entering it in, you want to use parentheses to make sure you get it properly put in. So we'll do parentheses square root of x plus 5, close parentheses, minus 3, close parentheses, divided by, parentheses, x minus 4, close parentheses. And then we'll go ahead and we'll graph that. And you're going to see like the most underwhelming picture ever. It's just going to be this tiny little line. Got to make sure you use the parentheses, otherwise you don't get the picture right. But this is the picture you get. What this means is that we have to change the graphing window to see it properly. In this case, it's kind of hanging around close to the x-axis. So let's make y smaller. Y is now set from minus 1 to 10. Or so minus 10 to 10. Let's set it to minus 1 to 1. Yeah, what is it?
Were we allowed to make a table?
Absolutely, you could have, yes. Okay, I'm just showing it the way the book wanted you to do it. Okay, so now doing it from, changing the y to be from minus 1 to 1, we can get a better picture, and we get this really kind of lazy looking curve. Okay, now the first question it actually asks you is not for this limit. They do want you to find the limit and estimate it. They also want the domain of the function. Clearly here, what's the domain going to be?
Negative 4 or negative 5.
So x is going to be equal to or greater than negative 5, and x cannot be what?
0.
Not 0.
4.
4. Because remember, if I stick 4 in this thing, it breaks down. Okay? So we'll go ahead and we'll note that. So our domain here is going to be x greater than or equal to negative 5 x not equal to, not negative 4, excuse me, positive 4. Okay? Yeah. There we go.
They wrote a different notation in the back of the book when I checked my answer.
Okay.
They're like a U.
They used interval notation.
Yeah, that's what.
Yeah. And that's fine. That's okay. Remember, the idea is to be able to express the what you're getting at in whatever way makes sense most. Okay. Probably the best way is just to write it out by hand. Remember. Okay. The domain is this. Yes, Roy.
What window did you put again? Just trying to see the entire picture.
I'm sorry.
What window did you put?
Oh, I changed the y-axis to go from -1 to +1. So my y minimum is -1. My y maximum is 1. That's how I got this picture.
You left the axis.
X I just left alone.
Okay.
Yes, you may. Okay. All right. Now comes the important question, which is, okay, we ultimately want to know what the limit at 4 is. Okay? How do we figure that out? Well, we can make a chart. That's one good way of doing it. Using the calculator, though, we could do it fairly quickly by asking it just to give us values around 4, and then we estimate. So, doing it that way, if you hit the trace button, you could just directly ask it for values. So, for example, what's a value of x less than 4 but really close to 4?
3.9. No.
So 3.999 is the one I'm going to test. Okay. We actually don't need to do a lot of points. Really, just 2 are fine. 3.99, which gives us 1.6666713. Okay, so 1.667, if you will, 1.67. Okay, and if we do it right above 4.001, we also get 1.6666204, or 1.67. Okay, so what's this thing going to approximately equal then? 0.167. By the way, what's that actually as a fraction? Anybody know?
1/8.
Okay, it is not 1/8. It's 1/6, I believe. Someone
That's
said.
that's 5/3. No,
Okay.
no, I'm an idiot.
This should be roughly 1/6. Okay, and that's actually what this limit does come out to be. Okay, so if you were to get it as close as possible, you would get an answer of 1/6. And I'm just going to double check that real fast. Yeah. Okay. So our limit ends up actually being 1/6 here. Okay. Any questions how that works now? See how you can use the calculator to figure out the answer. By the way, the rest of this, by the way, it asks like, what's the problem with using the calculator? Is there a possible error? Yada yada yada. The error in this one would happen if you left the picture originally as it was. You wouldn't see that, for example, the original picture makes it look like it's only defined from -5 to 4, and it doesn't include the stuff beyond 4. Okay, because you're so zoomed out from it. Okay, so you do have to play around with the calculator picture. I saw a hand up.
Yeah.
Yes.
I'm not sure I'm putting in wrong. I guess I'll just ask you after class.
Okay.
I'm not getting the same graph.
Not saying it's super. Chances are it has to do with parentheses around your numerator and denominator. Things.
Okay.
All right. Okay. Any other questions about the homework? We good? Excellent. Moving on then, we're going to finish talking about the analytical solving limits analytically. Okay, and we're actually going to go ahead and I went ahead and did this. Excuse me. Look at all the various properties that limits have. Okay, and so here we go. All right. We're going to look at the properties of limits, and we're going to start with 3 basic limits, okay, and see sort of examples of these. These are all going to be properties and tricks to help you calculate a series of limits quickly. Your finger okay?
Yeah.
Okay. Gotcha. All right. And so that's what we're after here, okay? So the first one, kind of the first property or basic limit we're looking at, these actually, well, whatever. Is that the limit of a constant is a constant. Okay, it's the same constant. That is, if I take the limit as x approaches c of some constant b, I get b as my answer. So I have an example to the side, a rather ridiculous one, the limit as x goes to 80 of 2 is 2. Okay? Constants, again, the limit of a constant is the same constant. Nothing really changes there. Constants are kind of trivial, okay, in that regard. So that's our first basic limit. Our next basic limit is fairly self-explanatory. The limit as x approaches c of x is c. That is, if my function is just x, the limit is the value of the function. Okay, limit as x goes to 5 of x is equal to 5, for example. Okay, any questions there? These should be super straightforward. Okay, the last one. If n is some sort of integer, okay, then the limit as x goes to c of x to the n is c to the n. Okay, thus, example, as x goes to 2 of x cubed, that'd be 2 cubed, which is 8. Okay, these are some of the very basic limits you'll ever see. Why these are so useful is these, combined with some of the other properties we're about to see on the next page, basically tell you something we kind of said yesterday, that the limit of a polynomial is always equal to whatever the polynomial is evaluated at. Okay, that is, if I do the limit, it's like x approaches c of f of x, and f of x is a polynomial, then the answer is just f of c. Okay, kind of a nice way of calculating these things out. Okay, these properties help us establish that. Any questions about how any of these work right here? They're fairly easy and straightforward. Yes, they're too simple almost. Okay. Let's look at some more properties. Now for these properties, we're going to make an assumption. The assumption we're going to start with is that the limit as x goes to c of f of x is equal to L, and the limit as x goes to c of g of x is equal to k. And L and k here are just numbers, okay? So it'd be like saying, the limit as x goes to 5 of f of x is 10, okay? That sort of idea, all right? That's all we mean by the L and k here. They're just numbers. Any problems with that kind of notation? All right. Then we can go through here and we can see some special properties the limit has. The first one is a scalar property. That is, if I take the limit as x goes to c of a function times a constant, in this case constant b times a function, it would be the same as if I did it constant b times the limit of that function, or just b times the answer. Okay, b times L. Everyone see how that works? What this means is that a constant that I'm multiplying by can be pulled in and out of the limit at will. Okay, that ends up going to be a very important feature later on. In fact, there's some derivatives that we can take the answer to quickly by recognizing that that is the case, and we can just pull out the constant. We're going to see what a derivative is soon, and it ends up being based off the limit. So ends up being an important property. Any problems with that? Okay. Next up, all right, will be ones that are basically a bunch of properties that are suspiciously similar to properties about evaluating a function or two functions together. They're very much the same, okay? Our first one is an additive subtractive property. I didn't label it that, but whatever, okay? That the limit as x approaches c of f of x plus or minus g of x would be like doing the limit separately and then adding or subtracting the results together. Any questions about that? Okay, so how these things come in handy would be like, well, your typical polynomial is usually something like x cubed plus 2x plus, something. The limit, I can take that all at once, or I can do each one separately and get the same result. Okay, which is basically what this says. Okay. Our next property is a multiplicative property. If I multiply the two functions together, it's like I multiply the limits together. Okay. Limit as x goes to c if the two functions multiply together is like if I did the limit separately and multiplied them together. Okay. You get L times k at the end. Okay. Again, that should not be anything crazy. That's exactly what we should expect. We've seen that before with functions, right? Yeah. Should be no issue. Okay. I'm going to scroll down a little bit here, so those of you writing. Hold up a second. Tell me where to stop. We're good, we're good. We keep good? Still good?
Where do you get that K from on 6?
The K on 6, again, it's the same K up here. From the very beginning, we established that we'd have that K. Okay? Alright. So, we got that. Now, next we've got, next property has to do with division. Okay? And we've got the limit as x goes to c of f of x divided by g of x is equal to, essentially, the two limits divided by each other. Okay? The one thing I left out here that the book has when it covers this is it also says, granted, that the limit as x approaches c of g of x isn't 0. Okay? Now, that's understandable why they want to do that, but really, if it were 0, what would it just mean?
Undefined.
Not undefined. Remember, we're talking about limits.
Oh, the limit would be 0?
Not 0. Does not exist. Just mean there is no limit there. The math otherwise works exactly the same way. So kind of saying, oh, we can't have g of x be 0 is kind of being nitpicky there. If it were 0, it just means we don't have a limit. But that's good, right? That's an answer just as fine as any other. Okay? So that's why I left it off there. But otherwise, the mechanics behind it work the same exact way. Okay? Any questions about that one? Okay. And lastly, if I raise a limit to a power, it's like I'm raising the entire thing to a power. So limit as x goes to c of f of x to the n is like I take that entire limit and raise it to the n power. Okay. Again, nothing here should be all that shocking. These are all the same things that you see when you're looking at functions being evaluated. Okay. They work almost identically. All right. Any questions? Want you guys copy and finish this out. I'm going to have to flip the video. The video is, I don't know why it mirrors it. It wasn't mirroring it the other day, by the way. It made it nice and normal, so. Something about the iPad. Huh? Oh. I think, I have a sneaking suspicion it has to do sometimes with when I flip the iPad upside down and has to change the orientation, for some reason it may not like to change the camera.
If you like lock it, and then you can lock the orientation.
I could.
I don't know.
It's weird. It doesn't want to play right. Alright. What I just need to do is get a camera in here and just film myself that way. So, alright. Any questions so far? Good.
Will that be on the canvas?
Yes. These notes are already on canvas, in fact. Okay. One thing about all this, by the way, is all these properties together with those first basic ones, notice how they would establish that rule before, that the limit of a polynomial is just equal to whatever the polynomial is, okay, at that point. All these properties would make that happen, so they're kind of nice at converting that what we had noticed the other day. The other thing, too, is it's just polynomials that this would help you out with. What other type of function would this make possible that would just plug and chug, essentially? What other type of, what function? Rational functions, yes, okay? It also makes rational functions work, because remember, a rational function is just a polynomial divided by another polynomial, and so these here, if these rules make it work for all polynomials, they should also make it work for all rationals as well. And again, the whole notion that, well, if I divide by 0, it doesn't exist, well, that's fine. We can have that be, remember, does not exist is a perfectly fine answer, okay? As far as we're concerned. It's like that good, it's good. You don't have to deal with anything else, okay? All right. We talked yesterday about what happens with a function involving a radical, okay? The last things we should kind of take a look at here is, let's see, we already talked about squeeze theorem. Kind of the last of these properties we might want to investigate is what happens with composite functions, okay? If you remember, from pre-calculus, a composite function is when I stick one function in for the other, okay? So it'd be like if I had two functions, f of x and g of x. The composites I could get from there would be f of g of x and or g of f of x. Those are the two ways I can combine those. That is, I'm sticking one function in completely for the other. Okay. Turns out that the limit of a composite function, okay, ends up working out fairly simply as well. If I did the limit as x goes to c of f of g of x, that'd be like me just doing f of the limit as x goes to c of g of x, which should just be f of L, okay? Given, of course, that the limit of g of x is equal to L. Okay. I'm sorry? Nope. Good? Okay. So it's sort of another way of thinking these things through. Okay? Any questions about that?
So you kind of call it F that you can move anywhere?
It's not going to be. It's not quite like a scalar like that. Remember, these are composite functions.
But it acts like
But it's going to kind of act the same way, yeah. Or at least give you a sense that you can kind of shorten things up a bit. Let's take a look at that, okay? Let's look at an example of this in action, and you'll get the idea. So our example here will be, let f of x be equal to like 3x squared plus 2. G of x is equal to 4x minus 1, okay? Well, then the limit as x goes to, I don't know, 0 of f of g of x, we could rewrite this, really, I could just figure out what the limit as x goes to 0 of this is, and just plug that into f of x. So this is really f of the limit as x goes to 0 of g of x, which will be f of negative 1, which then gives me 3 plus 2, so 5. Okay? So it's essentially just like composites. Okay? Works no differently really there. Okay? Again, if you think about it, that should make sense the way a composite function works. Okay? Remember, if I stick in, when you evaluate a composite function, if I did, let's say, what's f of g of 5, I'm essentially figuring out what g of 5 is, and sticking that answer into f of x, okay? Well, same deal here, except we're doing it with a limit instead, okay? Any questions about that? Okay, it's a fairly straightforward thing. Okay. All of these together should make it a lot easier to start calculating out how to do a limit analytically, okay? So, if nobody has any questions about this, we could go ahead and move on and start getting ahead and looking at other stuff. So, are we all good on how this works? Okay, your homework tonight, okay, is going to be